Plate tectonics is a scientific theory describing the large-scale motion of Earth's lithosphere. The theoretical model builds on the concept of continental drift developed during the first few decades of the 20th century. The geoscientific community accepted plate tectonic theory after seafloor spreading was validated in the late 1950s and early 1960s. The lithosphere, which is the rigid outermost shell of a planet, is broken up into tectonic plates. The Earth's lithosphere is composed of 7 or 8 major plates and many minor plates. Where the plates meet, the relative motion determines the type of boundary: convergent, divergent, or transform. Earthquakes, volcanic activity, mountain building, and oceanic trench formation occur along these plate boundaries. The relative movement of the plates typically ranges from 0 to 100 mm annually. Tectonic plates are composed of oceanic lithosphere and thicker continental lithosphere, each topped by its own kind of crust. Along convergent boundaries, subduction carries plates into the mantle. The material lost is roughly balanced by the formation of new crust along divergent margins by seafloor spreading. In this way, the total surface of the lithosphere remains the same. This prediction of plate tectonics is also referred to as the conveyor belt principle. Earlier theories propose gradual shrinking or gradual expansion of the globe. Tectonic plates are able to move because the Earth's lithosphere has greater strength than the underlying asthenosphere. Lateral density variations in the mantle result in convection. Plate movement is thought to be driven by a combination of the motion of the seafloor away from the spreading ridge and drag, with downward suction, at the subduction zones. Another explanation lies in the different forces generated by tidal forces of the Sun and Moon. The relative importance of each of these factors and the relationship to each other is unclear and still the subject of much debate. Key principles. The outer layers of the Earth are divided into the lithosphere and asthenosphere. This is based on differences in mechanical properties and in the method for the transfer of heat. Mechanically, the lithosphere is cooler and more rigid, while the asthenosphere is hotter and flows more easily. In terms of heat transfer, the lithosphere loses heat by conduction, whereas the asthenosphere also transfers heat by convection and has a nearly adiabatic temperature gradient. This division should not be confused with the chemical subdivision of these same layers into the mantle and the crust. A given piece of mantle may be part of the lithosphere or the asthenosphere at different times depending on its temperature and pressure. The key principle of plate tectonics is that the lithosphere exists as separate and distinct tectonic plates, which ride on the fluid like asthenosphere. Plate motions range up to a typical 10 to 40 mm per year, to about 160 mm per year. The driving mechanism behind this movement is described below. Tectonic lithosphere plates consist of lithospheric mantle overlain by either or both of two types of crustal material: oceanic crust and continental crust. Average oceanic lithosphere is typically 100 km thick. Its thickness is a function of its age. As time passes, it conductively cools and subjacent cooling mantle is added to its base. Because it is formed at mid-ocean ridges and spreads outwards, its thickness is therefore a function of its distance from the mid-ocean ridge where it was formed. For a typical distance that oceanic lithosphere must travel before being subducted, the thickness varies from about 6 km thick at mid-ocean ridges to greater than 100 km at subduction zones. For shorter or longer distances, the subduction zone thickness becomes smaller or larger, respectively. Continental lithosphere is typically tilde 200 km thick, though this varies considerably between basins, mountain ranges, and stable cratonic interiors of continents. The two types of crust also differ in thickness, with continental crust being considerably thicker than oceanic. The location where two plates meet is called the plate boundary. Plate boundaries are commonly associated with geological events such as earthquakes and the creation of topographic features such as mountains, volcanoes, mid-ocean ridges, and oceanic trenches. The majority of the world's active volcanoes occur along plate boundaries, with the Pacific Plate's Ring of Fire being the most active and widely known today. These boundaries are discussed in further detail below. Some volcanoes occur in the interiors of plates, and these have been variously attributed to internal plate deformation and to mantle plumes. As explained above, tectonic plates may include continental crust or oceanic crust, and most plates contain both. For example, the African plate includes the continent and parts of the floor of the Atlantic and Indian Oceans. The distinction between oceanic crust and continental crust is based on the modes of formation. Oceanic crust is formed at seafloor spreading centers, and continental crust is formed through arc volcanism and accretion of terrains through tectonic processes, though some of these terrains may contain ophiolite sequences, which are pieces of oceanic crust considered to be part of the continent when they exit the standard cycle of formation and spreading centers and subduction beneath continents. Oceanic crust is also denser than continental crust owing to the different compositions. Oceanic crust is denser because it has less silicon and more heavier elements than continental crust. As a result of this density stratification, oceanic crust generally lies below sea level, while continental crust buoyantly projects above sea level. Types of plate boundaries. 3 types of plate boundaries exist, with a 4th mixed type, characterized by the way the plates move relative to each other. They are associated with different types of surface phenomena. The different types of plate boundaries are: transform boundaries occur where two lithospheric plates slide, or perhaps more accurately, grind past each other along transform faults, where plates are neither created nor destroyed. The relative motion of the two plates is either sinistral or dextral. Transform faults occur across a spreading center. Strong earthquakes can occur along a fault. The San Andreas Fault in California is an example of a transform boundary exhibiting dextral motion. Divergent boundaries occur where two plates slide apart from each other. At zones of ocean-to-ocean rifting, divergent boundaries form by seafloor spreading, allowing for the formation of new ocean basin. As the ocean plate splits, the ridge forms at the spreading center, the ocean basin expands, and finally, the plate area increases, causing many small volcanoes and/or shallow earthquakes. At zones of continent-to-continent rifting, divergent boundaries may cause new ocean basin to form as the continent spreads. The central rift collapses, and ocean fills the basin. Active zones of mid-ocean ridges and continent-to-continent rifting are examples of divergent boundaries. Convergent boundaries occur where two plates slide toward each other to form either a subduction zone or a continental collision. At zones of ocean-to-continent subduction, the dense oceanic lithosphere plunges beneath the less dense continent. Earthquakes trace the path of the downward-moving plate as it descends into asthenosphere. A trench forms, and as the subducted plate is heated, it releases volatiles, mostly water from hydrous minerals, into the surrounding mantle. The addition of water lowers the melting point of the mantle material above the subducting slab, causing it to melt. The magma that results typically leads to volcanism. At zones of ocean-to-ocean subduction, older, cooler, denser crust slips beneath less dense crust. This causes earthquakes and a deep trench to form in an arc shape. The upper mantle of the subducted plate then heats and magma rises to form curving chains of volcanic islands. Deep marine trenches are typically associated with subduction zones, and the basins that develop along the active boundary are often called foreland basins. Closure of ocean basins can occur at continent-to-continent boundaries. Collision between masses of granitic continental lithosphere. Neither masses subducted plate edges are compressed, folded, uplifted. Plate boundary zones occur where the effects of the interactions are unclear, and the boundaries, usually occurring along a broad belt, are not well defined and may show various types of movements in different episodes. Driving forces of plate motion. It has generally been accepted that tectonic plates are able to move because of the relative density of oceanic lithosphere and the relative weakness of the asthenosphere. Dissipation of heat from the mantle is acknowledged to be the original source of the energy required to drive plate tectonics through convection or large-scale upwelling and doming. The current view, though still a matter of some debate, asserts that as a consequence, a powerful source of plate motion is generated due to the excess density of the oceanic lithosphere sinking in subduction zones. When the new crust forms at mid-ocean ridges, this oceanic lithosphere is initially less dense than the underlying asthenosphere, but it becomes denser with age as it conductively cools and thickens. The greater density of old lithosphere relative to the underlying asthenosphere allows it to sink into the deep mantle at subduction zones, providing most of the driving force for plate movement. The weakness of the asthenosphere allows the tectonic plates to move easily towards a subduction zone. Although subduction is thought to be the strongest force driving plate motions, it cannot be the only force, since there are plates such as the North American plate which are moving, yet are nowhere being subducted. The same is true for the enormous Eurasian plate. The sources of plate motion are a matter of intensive research and discussion among scientists. One of the main points is that the kinematic pattern of the movement itself should be separated clearly from the possible geodynamic mechanism that is invoked as the driving force of the observed movement, as some patterns may be explained by more than one mechanism. In short, the driving forces advocated at the moment can be divided into three categories based on the relationship to the movement: mantle dynamics related, gravity related. Driving forces related to mantle dynamics. For much of the last quarter century, the leading theory of the driving force behind tectonic plate motions envisaged large-scale convection currents in the upper mantle, which can be transmitted through the asthenosphere. This theory was launched by Arthur Holmes and some forerunners in the 1930s and was immediately recognized as the solution for the acceptance of the theory as originally discussed in the papers of Alfred Wegener in the early years of the century. However, despite its acceptance, it was long debated in the scientific community because the leading theories still envisaged a static Earth without moving continents up until the major breakthroughs of the early 60s. 2- and 3-dimensional imaging of Earth's interior shows a varying lateral density distribution throughout the mantle. Such density variations can be material, mineral, or thermal. The manifestation of this varying lateral density is mantle convection from buoyancy forces. How mantle convection directly and indirectly relates to plate motion is a matter of ongoing study and discussion in geodynamics. Somehow, this energy must be transferred to the lithosphere for tectonic plates to move. There are essentially two main types of forces that are thought to influence plate motion: friction and gravity. Basal drag, plate motion driven by friction between the convection currents in the asthenosphere and a more rigid overlying lithosphere. slab suction, plate motion driven by local convection currents that exert a downward pull on plates in subduction zones at ocean trench. Slab suction may occur in a geodynamic setting where basal tractions continue to act on the plate as it dives into the mantle. Lately, the convection theory has been much debated as modern techniques based on 3D seismic tomography still fail to recognize these predicted large-scale convection cells. Therefore, alternative views have been proposed. In the theory of plume tectonics developed during the 1990s, a modified concept of mantle convection currents is used. It asserts that superplumes rise from the deeper mantle and the drivers are substitutes of the major convection cells. These ideas, which find the roots in the early 1930s with the so-called fixistic ideas of the European and Russian earth science schools, find resonance in the modern theories which envisage hot spots, mantle plumes which remain fixed and are overridden by oceanic and continental lithosphere plates over time and leave their traces in the geological record. Modern theories that continue building on the older mantle doming concepts and see plate movements as a secondary phenomena are beyond the scope of this page and are discussed elsewhere. Another theory is that the mantle flows neither in cells nor large plumes but rather as a series of channels just below the Earth's crust, which then provide basal friction to the lithosphere. This theory, called surge tectonics, became quite popular in geophysics and geodynamics during the 1980s and 1990s. Driving forces related to gravity. Forces related to gravity are usually invoked as secondary phenomena within the framework of a more general driving mechanism such as the various forms of mantle dynamics described above. Gravitational sliding away from a spreading ridge. According to many authors, plate motion is driven by the higher elevation of plates at ocean ridges. As oceanic lithosphere is formed at spreading ridges from hot mantle material, it gradually cools and thickens with age. Cool oceanic lithosphere is significantly denser than the hot mantle material from which it is derived, and slow with increasing thickness it gradually subsides into the mantle to compensate the greater load. The result is a slight lateral incline with increased distance from the ridge axis. This force is regarded as a secondary force and is often referred to as ridge push. This is a misnomer as nothing is pushing horizontally. Intentional features are dominant along ridges. It is more accurate to refer to this mechanism as gravitational sliding, as variable topography across the totality of the plate can vary considerably, and the topography of spreading ridges is only the most prominent feature. Other mechanisms generating this gravitational secondary force include flexural bulging of the lithosphere before it dives underneath an adjacent plate, which produces a clear topographical feature that can offset, or at least affect, the influence of topographical ocean ridges and mantle plumes and hot spots, which are postulated to impinge on the underside of tectonic plates. Slab pull. Current scientific opinion is that the asthenosphere is insufficiently competent or rigid to directly cause motion by friction along the base of the lithosphere. Slab pull is therefore most widely thought to be the greatest force acting on the plates. In this current understanding, plate motion is mostly driven by the weight of cold, dense plates sinking into the mantle at trenches. Recent models indicate that trench suction plays an important role as well. However, as the North American plate is nowhere being subducted, yet it is in motion, presents a problem. The same holds for the African, Eurasian, and Antarctic plates. Gravitational sliding away from mantle doming. According to older theories, one of the driving mechanisms of the plates is the existence of large-scale asthenosphere mantle domes which cause the gravitational sliding of lithosphere plates away from them. This gravitational sliding represents a secondary phenomenon of this basically vertically oriented mechanism. This can act on various scales, from the small scale of one island arc up to the larger scale of an entire ocean basin. Driving forces related to Earth rotation. Alfred Wegener, being a meteorologist, had proposed tidal forces and pole flight force as the main driving mechanisms behind continental drift. However, these forces were considered far too small to cause continental motion, as the concept then was of continents plowing through oceanic crust. Therefore, Wegener later changed his position and asserted that convection currents are the main driving force of plate tectonics in the last edition of his book in 1929. However, in the plate tectonics context during the early 1960s, the oceanic crust is suggested to be in motion with the continents, which caused the proposals related to Earth rotation to be reconsidered. In more recent literature, these driving forces are tidal drag due to the gravitational force the Moon exerts on the crust of the Earth, global deformation of the geoid due to small displacements of rotational pole with respect to the Earth's crust, other smaller deformation effects of the crust due to wobbles and spin movements of the Earth rotation on a smaller time scale. Forces that are small and generally negligible are the Coriolis force, the centrifugal force, which is treated as a slight modification of gravity. For these mechanisms to be overall valid, systematic relationships should exist all over the globe between the orientation and kinematics of deformation and the geographical latitudinal and longitudinal grid of the Earth itself. Ironically, these systematic relations studies in the second half of the 19th century and the first half of the 20th century underline exactly the opposite, that the plates had not moved in time, that the deformation grid was fixed with respect to the Earth equator and axis, and that gravitational driving forces were generally acting vertically and caused only local horizontal movements. Later studies, therefore, invoked many of the relationships recognized during this pre-plate tectonics period to support the theories of the many forces discussed in this paragraph. Tidal force is still highly debated and defended as a possible principal driving force of plate tectonics. The other forces are only used in global geodynamic models not using plate tectonics. Concepts are proposed as minor modulations within the overall plate tectonics model. In 1973, George W. Moore of the USGS and R.C. Ostrom presented evidence for a general westward drift of the Earth's lithosphere with respect to the mantle. He concluded that tidal forces caused by the Earth's rotation and the forces acting upon it by the Moon are a driving force for plate tectonics. As the Earth spins eastward beneath the Moon's gravity ever so slightly pulls the Earth's surface layer back westward, just as proposed by Alfred Wegener. In a more recent 2006 study, scientists reviewed and advocated these earlier proposed ideas. It has also been suggested recently in Lovett that this observation may also explain why Venus and Mars have no plate tectonics. As Venus has no moon and Mars' moons are too small to have significant tidal effects on the planet. In a recent paper, it was suggested that, on the other hand, it can easily be observed that many plates are moving north and eastward, and that the dominantly westward motion of the Pacific Ocean basins derives simply from the eastward bias of the Pacific spreading center. In the same paper, the authors admit, however, that relative to the lower mantle, there is a slight westward component in the motions of all the plates. They demonstrated, though, that the westward drift, seen only for the past 30 ma, is attributed to the increased dominance of the steadily growing and accelerating Pacific plate. The debate is still open. Relative significance of each driving force mechanism. The vector of a plate's motion is a function of all the forces acting on the plate. However, Therein lies the problem regarding the degree to which each process contributes to the overall motion of each tectonic plate. The diversity of geodynamic settings and the properties of each plate result from the impact of the various processes actively driving each individual plate. One method of dealing with this problem is to consider the relative rate at which each plate is moving, as well as the evidence related to the significance of each process to the overall driving force on the plate. One of the most significant correlations discovered to date is that lithospheric plates attached to downgoing plates move much faster than plates not attached to subducting plates. The Pacific Plate, for instance, is essentially surrounded by zones of subduction and moves much faster than the plates of the Atlantic Basin, which are attached to adjacent continents instead of subducting plates. It is thus thought that forces associated with the downgoing plate are the driving forces which determine the motion of plates, except for those plates which are not being subducted. The driving forces of plate motion continue to be active subjects of ongoing research within geophysics and tectonophysics.